2023 question number 3. So this question starts off with a little bit about amino acids. Now, it's useful to have, and you should have really, a basic familiarity with the concept of amino acids. So this is the generalized form of amino acid. The thing that changes for different amino acids is the R group, and we're talking about isoleucine, where the R group is this hydrocarbon chain. Now, the important thing to remember is that amino acids, obviously, part of it's an amine, part of it's an acid. So what that means is this part here can act as a base, and I can add a hydrogen, and that will be, or a proton, and that will become positive. And then this hydrogen here is acidic, so that will come off, and that will become negative. So depending on what kind of pH situation I'm in, either this will be protonated or this will be deprotonated. Okay, and then we are told what the R group is, and we're asked to draw the skeletal formula, draw the skeletal structure of isoleucine at pH 2. Now, this is a very acidic pH, and it's below both of these pKa values, which we'll come back to later. But at the moment, we can just think, well, if I'm in a very acidic situation, what is going to happen to my structure here? And obviously, if I'm in an acid, then this is going to act as a base, so I'm going to protonate this nitrogen here. So my first one, and remember this has to be drawn as a skeletal formula, or else it's not going to be valid. So I get my protonated amine group, so it's going to be positive, and then I can just draw the rest in the skeletal form, and it is CH with the methyl and then the ethyl chain. So that's the methyl. I'm not going to draw the H on because it's skeletal formula, and then with the ethyl group like that. Okay, and then I'm asked to do it at pH 11, which is very, very basic. So, excuse me, if I went very, very basic, what would happen? I would deprotonate. First, I would deprotonate here, and then I will deprotonate here. And because 11 is above my second pKa value, I've done both deprotonations. So I'm going to get H2N, hydrocarbon chain for R, and then the carboxylic acid is also deprotonated. So this is the form that I get in acidic conditions, and this is the form that I get in very, very basic conditions. In acidic conditions, this acts as a base, so I've protonated it. In basic conditions, this acts as an acid, I've deprotonated it. And then the isoelectric point is the pH at which the overall charge in the molecule is 0. Draw the skeletal structure of isoleucine at the isoelectric point. So if the overall charge is 0, then I must have protonated and deprotonated. So it's going to be H3N plus COO minus. Okay, and this is the zwitterion. Okay, and that is the form that's generally going to exist if you put it into just aqueous solution. And then it says calculate the isoelectric point of isoleucine. Now, you're not given any information about how to calculate the isoelectric point. I'm not a biochemist, which I assume this would fall under. You know, so at this point, you just got to have a stab, okay? And the only really thing that you can do is, well, I know that one pKa value is 9.6 and the other pKa value is 2.36, and I know if I'm below 2.36, I've protonated both groups. If I'm above pH 9.6, I've deprotonated both groups. So maybe the isoelectric point is just like the average of those two, and that's, you know, as much as I can. I know it's not really a great explanation. This is one of those things where if you know it, you know it. If you don't know it, you can sort of guess, but there's no real robust way to sort of work it out. So if I do 9.6 plus 2.36 divided by 2, it's going to be 5.98. Okay, and then we are told to confirm the pKa values. A 50 centimeter cube sample of 0.025 solution of isoleucine hydrochloride is titrated with 40 centimeters cubed of a 0.1 mole diluted solution of sodium hydroxide. Okay, so let's think very carefully about what's happening here. We have a solution of isoleucine hydrochloride. Okay, that is the hydrochloride salt. So let's think about what that means. That means if I take H2N, R group, carboxylic acid, and I'm reacting it with HCl to form the salt, what's going to happen? Well, this is a strong acid, so this is going to fully dissociate, and this is a weak base with this group here. So this is going to protonate this. How is it going to do that? It's going to do it here, H3N plus OH. Now that whole thing is positive. The whole thing is positive. I know I've got the double positive there, but don't worry about it. And then that forms the salt. So the counter ion is the Cl minus. So basically, I've got this thing. Okay, both the nitrogen of the amine and the oxygen of the acid are protonated. Okay, so I've got two acidic centers. I've got the carboxylic acid and then the protonated amine group. So when I do this titration with sodium hydroxide, it's going to first neutralize by deprotonating the carboxylic acid and then neutralize by deprotonating the protonated amine group. So there will be two equivalence points. Okay, so that's my first important piece of information, is I'm expecting two equivalence points. But before I even get to there, I can just be smart about it, right? I'm adding sodium hydroxide. So this titrant added here is NaOH. So once I get to 40, I've added 40 sodium hydroxide, and the concentration is much larger. So I should expect my pH at the end of the titration to be right up here. So I can immediately get rid of that one, get rid of that one, and get rid of that one. And I'm left with these three options. Now, I've already established that I should expect two equivalence points. The first one where I remove this from the carboxylic acid, and then the second one where I move it from the protonated amine group. This has only got one equivalence point, this point here, okay? And then it comes down to a 50-50. Now, this one here, you know, I don't know much about acid-base titration above the basics, but I've never seen a curve that does this straight away, you know, that goes right up here. So my inclination is to get rid of that one. Can I be a little bit more firm in that decision? Well, if I look at the quantities and the concentrations, I can do a C1 V1 equals C2 V2 calculation. So the concentration of my isoleucine is 0.025, 0.025, multiplied by my volume of isoleucine, which is 50, and then my sodium hydroxide is concentration 0.1, and then multiplied by my volume of sodium hydroxide that I would need to do the neutralization. Okay, and if I work that out, the amount of sodium hydroxide that I need to do the neutralization is going to be 0.025 times 50 divided by 0.1 is 12.5 centimeters cubed. So in other words, to reach my first equivalence point, I need 12.5 centimeters cubed of my sodium hydroxide. And you can see that's about where it comes out. So that's the one that I want. Okay. The other way of doing it is if you're, I mean, it depends how comfortable you are with pKa values. You know that the buffer region, so if I start here and here's my equivalence, my buffer region is going to be around my pKa value. So here, 2.36. And then I get a second buffer region up here, which is going to be about the same as my second pKa value of 9.6. So with those two pieces of evidence, I can sort of quite easily confirm that this must be the correct answer. Now, this is a very confusing situation, so I am going to do something that I don't usually do, which is I'm going to take a little aside here, just so we can be 100% sure we know what's going on at each of these pKa values. So this bit, we've already decided that one. This bit I'm just going to do on the back of here. So, excuse me. I am starting with the hydrochloride salt. Remember, it says isoleucine hydrochloride, and this is the hydrochloride salt here. So I've got H3N, this like that, my plus, and then I'm titrating it with the sodium hydroxide, and I get to my first pKa value. So what is actually happening at pKa 1, which is 2.36? Well, I'm forming H2N acid R group plus H plus. That's my first pKa value. Nope, that's completely wrong. So again, you see how easy it is to make mistakes on these things. So when I do the first deprotonation, you've got to decide which of these is going to be more acidic, and between the protonated amine group and the acid group, the more acidic one is going to be this one here. So let me just go ahead and change that. So that becomes positive, and then that, get rid of that. That is going to be my negative, okay? And then this obviously gives you the Zwitter ion form, which is the common form in sort of neutral water, which is how I just managed to spot that I'd made a mistake, because you wouldn't expect it to form the actual, both groups neutral is going to be unlikely. The neutral molecule is going to consist of the protonated amine group and the deprotonated acid group. So then the second neutralization point is going to be my H3N plus O minus, and then that, which is going to be pKa2, which was 9.60. So now this is going to be my second acid or acidic proton, is going to give me minus plus H plus. Okay, so I go from having the protonated amine to having the Zwitter ion. That's my first proton, and then I go from the Zwitter ion to the that'd be carbonate form, I guess, there. So that's what's happening at each of those pKa points. Now there's a whole branch of chemistry about this, which you can read about, but it's just very confusing if you've never seen this before. Hopefully that gives you a little bit more background to what's happening. If it doesn't, just ignore it. Okay, so let's carry on with the question. So it looks, at this point when you're doing this question, it's sort of, you think to yourself, we're doing organic chemistry. Let's see what happens next. But then, just like the last question actually, we do another pivot and we go into this bit of transition metal electron spin chemistry, which is always a pleasant transition to make. So you have this bit of information here, and then you're told that it forms a square pyramidal structure, which is why I've got this geometry here. And it says, complete the structures of the stereoisomers of copper-2 glycinate in the answer booklet representing the bidentate ligand as shown on the right. And there are 2 of these bidentate ligands, quite obviously. If you're not sure why that's obvious, I guess you could work out, you could see here from the number of carbons, if I've got 2 carbons in this ligand, I've got 4 carbons overall, I've got 1 nitrogen, I've got 2 nitrogens overall, okay? Or you could just see, well, if it's a bidentate ligand, I've only got 4 spots, so there must be 2 of them. So it says, complete the structures. If the stereoisomer is chiral, draw only 1 enantiomer, okay? So we go, and this is I sort of love and hate when they do this, when they give you 4 and they say not all boxes may be required. It's like it's a real bit of a teaser from the Olympiad people here. So we can just quite easily just go in and say, well, I can definitely have that. That's going to be 1 isomer. And then obviously I'm going to get another isomer if I just flip these around. Like that. Okay, and it should be pretty clear that there's no other way of arranging those. If I do any other kind of combination, I'm just going to get the same thing back. If I think to myself, let's say, for example, oh, what if I do this? What if I do NO there? And I do NO there? Then that is obviously just the same as that. Okay, so no. All right, these are my only two combinations. So that one is quite easy to visualize. Then we have something more complicated. So the amino acid methionine forms a methionine anion when deprotonated. In octahedral metal complexes, assume the methionine anion acts as a bidentate ligand through the nitrogen and carboxylate. So again, it's the same thing. But now I've got all three. Yeah, MMT3. So the easiest way to do this is just to go ahead and draw on three of them. So let's go NO, let's have that one. Let's go NO, that one, and NO, that one. Okay, so when it comes to these octahedral complexes, when we're talking about chirality, so when we're talking about isomerism with octahedral complexes, the really important thing is to distinguish between the facial and the, I can't remember if it's called equatorial, I think it's equatorial, maybe it's got a different name, isomers. But what I mean by that is, look at the three nitrogens, okay? My nitrogen here, my nitrogen here, and my nitrogen here is all on one face. Okay, so remember, this is called octahedral because if you connect all the vertices, you get an 8-sided shape. Okay, so I've got a face here, I've got a face here, I've got a face here, and I've got a face at the back, and I've got the same 4 faces down at the bottom, so 8. Here I've got all of my nitrogens on one face. The other isomer is always going to be the nitrogens in a line. But what do I mean by in a line? I mean nitrogen there, and then instead of this nitrogen here, which puts them on the same face, I'm going to put the nitrogen there. So now they're all in a line. So I can just keep that one where it is, I can keep that one where it is, and I'll just flip this one around. Okay, now you can see that instead of nitrogens on the face, I've now got nitrogens all along the same plane. Okay, and therefore you know that these are not enantiomers. So you don't have to worry about this chirality situation here, because it says if the stereoisomer is chiral, only draw one. All right, these are not enantiomers because the nitrogen is in a different place, so they're not going to be mirror images. Now at this point, it is again time to think, well, is there any other way of drawing it which isn't a mirror image of one of these? So let me repeat that. Because it says only draw one enantiomer, the question is, can I draw another structure that is not a mirror image of one of these? And the answer is no. So I've got my facial, I've got my equatorial, and there's no other way of doing it. Okay? If you wanted to, you could try. Okay? So let's have a think. I can only have the nitrogens on the face or in a line, so the only other thing I can change about them is the way that they are connected. So let's go NO, 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 and let's go keep all the atoms in the same place, but can I connect them in a different way so that I get a different isomer? So let's connect that to that, that to that, and that to that. Okay, now we have to decide, is this different to this, or is it actually just the mirror image? So this one, well, the easiest thing to do is just to sort of bring this one up here and place them side by side. And you'll see that if you put this one up here, place them side by side, then this bit reflects this bit reflects this bit reflects this bit. So these are just mirror images. Now it might be that actually they're the same molecule, but I'm not going to bother trying to work that out, because whether it's the same molecule or whether it's just an enantiomer, it doesn't matter. The question doesn't want it. So I'm going to get rid of that one. Okay, and then we can do the same with this one over here. This one's a little bit more messy to draw, so if I connect those two together, then I have to connect this down to here, and this one up to here. Okay, and then we can try and decide whether or not this is a different isomer altogether. Now this one's a little bit more tricky to see. So what I'm going to do is I'm going to rotate around this axis by 90 degrees. So try and follow along if you can what's going on. So if I rotate it 90 degrees, I'm going to have my nitrogen there, my oxygen there, they stay the same place. Okay, so this one here is going to flip round to here, so I'm going to have that. Okay, this nitrogen goes to the back, and the oxygen is around there, and then this nitrogen comes to the front, and I've got that. Okay, so I've done that, and then what I'm going to do is I'm going to rotate it again 90 degrees in the same direction. So it's a little bit messy. If it's too messy the way that I've done it, you can just draw it out yourself. So this nitrogen now comes round to the right there. This nitrogen goes to the back. This oxygen comes down to the front, and then my last one is this oxygen goes around to the back, and that's onto this nitrogen here, and I get that. So I did 2 rotations, so I've rotated it by 180 degrees. What I've done basically is I've brought this nitrogen all the way around to the back, I've brought this nitrogen all the way around to the front, but importantly what you can see is this shows you that it is now the same isomer. So that is not a valid one either. Okay, it's a lot of work, you know. For these, I would just draw the facial, equatorial, and just be done with it. All right, but this is quite nice because this does sometimes come up with these octahedral isomer questions. So it's just nice to be able to manipulate them yourself in your head. Like I said, if this is a little bit too messy for you, have a go, draw it out yourself, and see if you can follow it through. Okay, all right. Then, after some lovely isomerism, which is always one of my favourites, we go to this d orbital splitting, which may be familiar to you, may not be familiar to you. So we have the degenerate d orbitals, and in the octahedral complex, this splits. And if you don't know about this, you should definitely go and read about it. It is fascinating. Sort of this is where the colour arises in transition metal complexes. We are then told that we can have either a high spin arrangement or a low spin arrangement. So if I've got 5 electrons, I can have them all unpaired. So the spins sum. So spin up, spin up, spin up, spin up, spin up, high spin. Here they cancel. Spin up, spin down, cancels. Spin up, spin down, cancels. Spin up. So here I've got 5 spin up. Here I've got 1 spin up. High spin, low spin. And then I'm given this equation here to work out the magnetic moment from the spins, because obviously you should be aware that this paramagnetism and diamagnetism arises from unpaired electrons. So the more unpaired electrons there are, the more magnetic it is. So then I've got this rhodium complex and this copper complex. I've got rhodium 3, I've got copper 2. And it says, complete in the answer booklet the number of d electrons. So if it's rhodium 3, okay, so rhodium is here. So it is going to be 5s2 4d7. So rhodium, I'm writing in red, rhodium is 5s2 4d7. But I've not got rhodium, I've got rhodium 3. So I'm going to lose my s electrons first, and then so I'm going to lose both of those and one of those, so I'm going to get 4d6. So number of d electrons in the outer shell is 6. And then it says, fill in the electrons in the d orbital diagrams. If there is the possibility of high and low spin arrangements, draw them both. Otherwise, just fill in the one possible arrangement. So, let's go with 6 electrons. 1, 2, 3. Okay, so those are my first 3 electrons. And then I can either go 1, 2, 3, 4, 5, 6, or I can go 1, 2, 3, 4, 5, 6. So let me show you how those look. There's that option, or I go 1, 2, 3, 4, 5, 6, like that. Okay, so this is my low spin, this is my high spin. Okay, now the spin magnetic moment, remember from this equation here, where n is the number of unpaired electrons. How many unpaired electrons are here? 0. So the spin magnetic moment here is going to be 0. Here I've got 1, 2, 3, 4. So it's going to be mu equals the square root of 4 into 4 plus 2. So 4 6s square rooted gives me 4.9. Now this is the kind of question that always comes up, where it's procedurally it's really simple. Like none of that was difficult to do, and you get 4 marks. So if you get it, it's fine. Just give away marks. Conceptually, it's quite difficult. Okay, because it's all this high spin, low spin stuff that you've never seen before, magnetic moments, weird equations, you know. So conceptually, it's quite difficult. But once you have just followed the instructions and you do the process, it's actually really straightforward. And they're going to give you 8 marks. 8 marks for this. You know, if you get just this section, just question 3 part F, you're already, you know, almost at a bronze award if you can just figure this bit out. Okay, so then it says to do the same for copper. So copper is here, so it's 4s2 3d9, 4s2 3d9, but we should be a little bit careful because we know that actually it's not that, it's 4s1 3d10, and then, although it probably doesn't make a difference in this case, copper 2 is going to be, I lose my s electron and I lose one of my d electrons, so it's going to come out as 3d9. Okay, so then I go, number of d electrons in the outer shell, 9, and then 1, 2, 3, 4, 5, 6, 7, 8, 9. So, as you can see, there's no other way of writing this electron arrangement. Okay, if I've got 9 electrons, I can only have 1 unpaired electron. So there's no other possible arrangement. Alright? Because no matter how I write it, I will always have only 1 unpaired electron. So there's no need to fill any of that in. Okay? And then I've got 1 unpaired electron, so mu equals the square root of 1 into 1 plus 2. So, excuse me, so this is 3, so this is just root 3. Root 3 is 1.73. Okay, and then we come to the last part, which is the spin magnetic moment observed experimentally for iron 3 is 5.63. Determine whether the metal is high spin or low spin. Now we're told up here that for iron 3, this is the high spin arrangement, this is the low spin arrangement. So for the high spin arrangement, I've got n equals 5. For the low spin arrangement, I've got n equals 1. So high spin would be n equals 5. Low spin would be n equals 1. Now, my initial temptation is to work this backwards. So I know that mu equals the square root of n into n plus 2. And I'm given 5.63 equals mu, so then I can just work out, and I can solve that for n. So I would 5.63 squared equals n squared plus 2n, which is then, you know, minus 5.63 squared 31.7 equals 0. Do the quadratic formula, so you get minus 2 plus or minus the square root of b squared, take 4 times 31.7 over 2. Let's just go ahead and do it all. So you get 4 times 31.7 plus 4, root that. You can't do the minus 2 minus that, so it's going to be minus 2 plus that. So take 2, divide by 2, and you get 4.7. So n equals 4.7. Okay, so doesn't come out exactly as n equals 5 or n equals 1, but it comes out pretty close to n equals 5. The other way of doing it, which admittedly is probably slightly easier, is you just put n equals 5 into here, and you put n equals 1 into here. So if I put n equals 5 in, if I do mu equals square root of 5 into 5 plus 2, or I do mu equals 1 into 1 plus 2, then I get my two answers. So 5 times 7 square root, 5 times 7 square root gives me 5.91, or again root 3, 1.73. Whereas my answer is 5.63, so it's going to be much closer to this one. So, high spin. The trick there being that it doesn't come out exactly, but it's close enough that you should be able to go for high spin. All right. Again, I don't know how they managed to go from amino acids, isoelectric points, all the way through to high spin, low spin, transition metal complexes, but good job, people writing these questions.